sort of went around the Oceanographic Data Center saying, well, what are other people doing, and what should my group be doing? How should we organize ourselves, and what should we give priority to? And this has actually turned out to be, I'm getting this widely applicable across our center, so we now use it. So I'm going to talk about scientific data stewardship. And I was trying this morning, actually, while I was stuck on the red line, to think about how I characterize the differences between them. But I think one of the things that we often take for granted and we don't elucidate is that scientific data stewardship really requires human interaction to a high degree, and perhaps a higher degree than archive of textual information, because it is so specialized. It is completely useless without an expert to interpret it for you. So very much of what we do involves interacting with the data to try and retain that expertise for the long term on behalf of our nation and world. So we have application of an integrated suite of functions that enable the full value of the data to be preserved and exploited over the long term. Our minimum default preservation horizon is 75 years, or as long as the data shall remain scientifically significant and useful. So I tend to think that's as long as we shall have people on the earth. A very long time horizon. So there are 5 things that you need to have. Basically, you need to document the data and preserve it. You need to have provenance. That comes under digital preservation. You need to provide IT support so that you can maintain the integrity. You can provide access in flexible ways that evolve over time. You also need to be able to work with the data. So that's one step, which is why I labeled that as digital preservation plus. You need to assess and ensure data quality. This is the driest part of my talk, I assure you. You need to engage with the scientific community that the best understanding is applied to the data. And that requires subject matter expertise, and you need continuity over the long term, and you need, of course, to pay attention to your media and things like that. So this is the conceptual model that I came up with when I was casting about for what do we do and what do we do about it. And really the archival part, the curatorship, is the very bottom level, and then much of our other activities are built on top of that. So we have long-term preservation access, and I'm going to walk through these with examples. We have tailored access, which is tends to be, I think, a little more heavily emphasized in the science world because we have very large data sets, right? We're talking about hundreds of terabytes size data sets. I think last time I heard NASA has about 13 petabytes on hand, and we have about 11 in NOAA. So, I mean, these are massive collections of data. Scientific quality assessments, deriving products usually out of aggregates of data that would not necessarily be available to individual researchers around the world. Building climate data records, that's long-term connected series of stuff. And then various things on the national service level. So, and these are organized in requiring increasing subject matter expertise. So this was based on the NDSA levels of digital preservation. I actually went and sat down with our lead archivist, who is trained in information science, unlike me, and said, you know, how do we come out on this scale? Because I work with this, but I do tend to take it on faith that the people who have formal training in this are doing their job and it's done right. We've got some areas to improve, particularly in formats and geographic location. I don't think we maintain 3 copies of everything. So to level 1, we bring in data and we have checksums and we make sure that it is actually preserved. Typically it goes to 2 geographic locations. It's replicated on tape. It's kept on spinning disk if we think it's valuable enough. The next thing we do is try and provide tailored access, and by that I mean you have hundreds of terabytes and you want just a slice, or you're studying one particular geographic area. How do we provide that to you? So we spend a lot of time thinking about this. Another thing that we do is a lot of automated quality monitoring. NOAA has 17 satellites in the air right now. Some of those are on standby because we're an operational agency, so they're replicates of each other and they're just waiting. But many of them are actually operating, and one of the things we need to know is, you know, was there a calibration slip in 2011? And we need to be able to present that to people succinctly, so you can see the little arrow that I have there shows, in fact, where there was a calibration slip in one of our satellites that's flying out. And in the plot on the left, it shows you there's a missing chunk of data, and you'd be able to go back to the logs and find out why that happened, because it might affect the science you're trying to do. The next thing we try to do is actually, if you have a bunch of measurements that are the same type, what can you do? So one of the things that quickly becomes apparent, particularly with in situ data that we collect, is well, actually, I'll take that back. One of the things that becomes apparent when you have collections of data, thank you, is You have biases. So you may have a particular class of instruments that was deployed, and then somebody, whatever company comes up with the new model, and it turns out actually that there's a measurement bias between the two. And this is a picture of one. This is an ocean profile. But the same thing happens with satellites, and typically we handle that by having satellites overlap in time. We launch one before the last one fails. That's not always possible, but that's the intent. And another thing you can do when you have loads and loads of data, as opposed to being an individual researcher with just one collection, is you can characterize a piece of data in relation to a very large aggregate. Is it typical? Is it atypical? That again gives you more insight into the significance of the measurement and what may be going on. The next thing that we do with the data is actually create aggregated products. And again, this is all oriented toward providing enhanced access. Many researchers do not have the technical know-how or the IT infrastructure to handle, the 21 million temperature profiles that we have on hand, for example, or the 17 satellite missions. So we do things like make climatologies for them. So if you're a state fisheries manager, staff assessment manager, you might be able to go in and get one of our climatologies, and you could then take your most recent survey and you could characterize it with respect to the long-term mean, because we've provided that long-term mean. So we do a lot of that kind of activity. At the next level up, we create records that are de facto standards. Sometimes they're officially sanctioned standards. We have one that we produce, which is an official NOAA climate data record. It's called Pathfinder Sea Surface Temperature, and it's based on the intercalibration of advanced very high radiometer something from 8 satellites. If I was going a little slower, I could do it. But so we've intercalibrated 8 different satellites to make a 31-year time series of global sea surface temperature, which is it's a really important environmental record for everything from coral bleaching to fish stocks to water quality along the coast. It was before it was declared as an officially sanctioned climate data record. It was a de facto standard for many municipalities, cities, states, and nations. And at the highest level, we provide national service. An example of this would be at our sister permanent archive, the National Climatic Data Center. They make the climate normals when the Weather Service comes out and says the summer exceeds any records and is 3 standard deviations higher than the climate normal. They're the ones who actually went through and took 30 years of weather data and decided what's the average, what is our average weather across the nation. So one of the things that we do is the scientific community has kind of come around a format called NetCDF as a standard, and there are a couple of conventions that are very widely used, thank you, called Climate Forecast Compliance and Attribute Conventions for Dataset Discovery. So we take those and we basically have said, well, there are 8 different kinds of oceanographic data that you might have, and here is a template. If you're going to submit data to us and you use this template, we can ensure that it will be widely understandable, widely discoverable, and able to be supported by a lot of automated protocols that we have. This is an example, more on the IT level, of what automated protocols we support. File transfer protocol, hypertext transfer protocol, most people don't even know what that means. Data access protocol, that's a very wonderful way of slicing and dicing your data, and our average data set that someone comes in and uses that protocol to access is about 100 times larger than our average data set in a whole, and they're usually subsampling something like 1/10,000th of it. So it lets you pinpoint what you want. We have a live access server, we support GIS, we support Google Earth with KML layers, web coverage service, web mapping service, all these different kinds of services. Again, it's a way to let the community access the data in a way that they're familiar and comfortable with it, so that they can spend their time doing the best interpretation of the data. And that's just a cute graphical view of our GeoPortal, which becomes a platform for all these different services that we deploy. And thank you very much.